Okay, here we are. Today we're gonna cover alkanes. This is topic 10.2 of the IB standard level curriculum. You can find this in the IB Chem guide, which is posted online. You can see the points we're gonna talk about listed here. We'll do them in order. So I would encourage you to watch this as many times as you need to. There are some sample questions on the website that will help us or help you to practice some of these skills. So you can see we're going to talk about the reactivity of alkanes in a couple ways, in a general sense here, and then in some specific ways with combustion and this process of chlorination and bromination. So the first thing we're going to talk about is the reactivity of alkanes. So if you recall, alkanes are organic compounds that have nothing but carbon to carbon single bonds and carbon to hydrogen single bonds. Well, it turns out that those bonds are extremely strong, and in addition they have a very nonpolar nature. And what that means is that the electrons shared in the bond are shared fairly equally. So if I take an example of the simple 2-carbon ethane, if we are to break this bond here, because the electrons tend to be shared equally, the tendency is for those electrons to be distributed equally, one to each carbon. That's a compound that is very unstable. If you were to continue, if you were to draw the valence structure of this compound, it would be the elemental form of carbon. Of course, these would be occupied as there would be hydrogens attached here, but that single bond in that location to the right, let me get rid of this for us, that single bond single electron here is extremely reactive. And if you remember what we discussed, if something is extremely reactive, that means it's very unlikely to be formed, or if it is formed, it will be very short-lived. It will react, as it will. So take those two things together, and that tells us that these carbon-to-carbon bonds here are extremely strong, and it's very unlikely that they will be broken. There are some reactions, however, that alkanes will undergo. One specific one is that of combustion. Now you see a few reactions here in this chart. The one on the top is a common combustion reaction, one that we've seen many times, where you take a hydrocarbon and you combust it with oxygen and you produce carbon dioxide and water. So this is known as complete combustion, where you completely sever these carbon to hydrogen bonds, which, based upon the previous slide, would release quite a bit of energy. These reactions tend to be extremely exothermic, because, as we said, the bonds between these carbons and hydrogens are fairly strong, and so breaking them does release quite a bit of energy because of their strength. So this process is known as complete combustion. It's recognized by the production of carbon dioxide and water. However, in the cases of what's known as incomplete combustion, you would get something similar to what's shown up here. Let's just focus on this here. The products are different slightly, and that is, in this case, you see that carbon monoxide is produced. This usually is a result of not enough oxygen. Perhaps it's oxygen is being fed in very slowly. This would also take place in under certain temperature conditions. Nevertheless, just please you're required to understand that incomplete combustion is the production of carbon monoxide as opposed to carbon dioxide, as shown here. In addition, one of the things that IB stresses is the fact that because this combustion reaction is so exothermic, it is used very commonly as a fuel source. So we know our gasoline engines, for example, use octane. So we burn propane in many cases as well. Natural gas is what we know that as. But because they produce so much energy, they're often used in a case of propane, to heat homes or in the case of both, you can actually run engines off of them because the energy released is so great. Well, in the process of doing that, if the combustion is not complete, if the oxygen, for example, is not fed in at a rapid enough pace, some of the byproducts we get are the aforementioned carbon monoxide. But in addition, because there is nitrogen already in the same air that is that carries the oxygen, nitrogen is approximately 78%, I think, is the number of the atmospheric air around us. So that nitrogen itself is fairly unreactive, but under the right conditions, especially very high temperatures, nitrogen will react with oxygen, as seen here, to form nitrogen monoxide, and you also see an example here of nitrogen dioxide. Those are could be considered products of an incomplete combustion as well, I suppose. And they are notable in that they are products that can lead to some very damaging atmospheric effects. In the case of nitrogen monoxide here, nitrogen dioxide here, it's easily shown that it can react with water to form nitric acid. And that nitric acid, this water would be in the atmosphere, for example, this nitrogen dioxide released by your engine, they could react in the atmosphere to form nitric acid, and this is what's one of the causes of what's known as acid rain. So all in all, this process of combustion can have several detrimental effects. So acid rain being one of them. One that I have not mentioned, which is very common now, this is in the process of complete combustion. Carbon dioxide is a greenhouse gas. Carbon dioxide acts as a blanket, if you will. The heat, if you have the planet Earth, and the heat from the sun penetrates through the atmosphere, will reflects off objects and tries to escape back out to space. But this blanket, this atmospheric blanket, can sometimes keep that heat inside, so the temperature in the atmosphere does rise. That's the greenhouse effect, global warming, all kinds of phrases, but that's from carbon dioxide. And finally, another product of incomplete combustion that's not listed here on the screen is that of just carbon, otherwise known as soot. And that particulate can get into the lungs, it can poison the soil, so it can cause quite a bit of damage. So moving on to the next topic, this is another specific reaction of alkanes. This involves halogens. The example seen below here is chlorine. However, we could apply the same thing to bromine. So you can see here in the curriculum point that you are required to know that this process for both chlorine and bromine. In both of these points you see chlorine and bromine here as well. So the model here is for chlorine, but it works exactly the same for bromine. And what you have here is, again, a process that creates something that is extremely reactive. This is similar to that carbon free radical I had discussed in the previous slide. This is a free radical of chlorine. So what we're seeing here is a molecule of chlorine, and it's undergoing reaction. And this reaction is initiated by ultraviolet light. Remember, ultraviolet light is light of high energy, because it has high frequency. So this ultraviolet light has enough energy to break these bonds, and what you see here is, again, what we call a homolytic fission. Homolytic means same cutting or equal cutting. Fission means splitting, I suppose you could call it that. So these two electrons in this bond here, when this bond is broken, they are shared equally between the two atoms. So you see that here. Now what we have here, again, this is elemental carbon, or excuse me, elemental chlorine. Well, remember, this atom wants an octet. It only has 7, so it's extremely reactive, as this one here. So this, in the atmosphere, for example, where ultraviolet light filters through the atmosphere, this process does occur fairly frequently in the creation of these free radicals. Now, that's an important thing. A free radical is a very reactive particle. So this process can initiate some very many other reactions. Any molecule around, for example, at that time can possibly undergo a reaction with one of these free radicals, because they are so desperate, so powerful, so reactive. However, the specific thing we're discussing here is the reaction of this free radical created by ultraviolet light, by the splitting of halogen, we're going to talk about the reaction of this with an alkane, specifically methane, which you see here, or ethane, both of which can be seen in the bullet points up here. So I'm going to demonstrate that with methane. It would be completely analogous using that of ethane, and remember, it would be completely the same if we just replaced every Cl with Br, bromine. So again, let's talk about this. This process of the reaction of a halogen with an alkane begins, as I said, with this production of this free radical. That step is typically known as an initiation step. You can see that listed right here. And initiation step is the production of a free radical. That starts the process off. Now that free radical can react with, as I said, just about anything. It can even react with itself. Of course, in the reaction of it with itself, it reforms that chlorine gas, which by itself is fairly stable and unreactive. That type of step, where a free radical reacts with another free radical, leaving behind no free radicals. Notice there is no other product here which can propagate this process. That's known as a termination step. So you see those down here at the bottom. So you can see the one I pointed out now, that the chlorines that were split homolytically could re-react with themselves. And you'll notice here that some of the other products formed earlier on that we haven't discussed yet can also re-react. But notice in each case here we have a radical reacting with a radical. Those are known as termination steps. So they stop the process. However, if those free radicals were not to react with each other, but if they were to react with objects around them, namely an alkane, this is so reactive it is enough to break this bond. Now please notice, look what you see here. This bond is being broken, and look, one of the electrons in that bond stays with carbon, one of them stayed with that hydrogen. That's a homolytic fission. This Cl and the electron that left with hydrogen are shared covalently in this bond. But look what's left behind. Another free radical. Now that free radical can then re-react with something else, like chlorine. So in the process of doing so, now in this case it's not the UV light, it's the high energy free radical splitting this, but again, it splits it homolytically. One electron here shared with this electron to form a bond, leaving behind a free radical, which can continue the process over and over and over and over. These are called propagation steps because they produce a product that can further react with something else. And if that further reaction produces again something that can react, this process would continue. So you can think of this as a type of chain reaction. Okay, so that is a quick summary, and there's a little citation there, or I took these images from. So that's information that's discussed here. So please refer to the guide and this lecture for more information. The last topic that actually I believe that's it. So if you have any questions, make sure you ask in class. You can email me, of course, and the next video we will record, or I will record, is that of 10.3, which is on the study of alkenes. So I'll see you then.